Hi, this is Jim Wright, and in this lesson we'll start looking at tilted work plane and how to use it. Our lesson plan is to discuss tilted work plane and describe what it is. I'll show you how to set up the machine coordinate system for a tilted work plane inside of NX or CAM Express. And then finally we'll use an example simulation machine that is shipped with NX or CAM Express to test our setup. First, a definition of the standard work plane. Typically, when we're talking about a 3-axis machining center, we're talking about these 3 axes. Z, of course, is the spindle axis. X is the longest linear axis that remains. And finally, Y would be the last linear axis. Now, these axes form planes, and the standard planes of work are shown on the screen. The G17 plane, typically described as the XY plane, is the one that we create arcs and circles in when the tool is in the Z direction. The G18 and G19 planes are the XZ and the YZ plane, respectively. The work plane can be defined as a location on the part. Typically we do this by setting up a program 000. Sometimes people will call that a work offset or a G54-0. Usually that's defined by the NC programmer where that location is, and then the setup person at the machine tool will physically dial in that location and make that the 000 position for this particular NC program. However, most machine cycles will only function in the work plane, or the plane that is normal to the XY plane. So if you're doing drilling or if you have any mill cycles, those only function in that specific work plane. There are also some 2.5 axis milling functions that only function in a specific plane, usually parallel to the work plane. For example, cavity milling. All cavity milling operations are performed with the cutting portion of the operation done perpendicular to the tool axis. So it's really a 2.5 axis milling operation. Same is true for face milling. Now inside of NX or CAM Express, we can change the tool axis to whatever we want it to be, but the remaining function, or the actual cutting motion, is still just 2.5 axis milling. The problem with that is, while we can do that within NX, the code becomes much longer at the machine tool, because now we're describing 5-axis motion for 2.5 axis milling capability. The NC control manufacturers saw this as a problem and then developed this new functionality called tilted work plane. What tilted work plane allows you to do is it allows you to define a new plane as the work plane, or what we would typically call the XY plane. This allows the code to be much shorter. It also allows us to use CAN cycles in a plane other than anything parallel to the XY plane. Now, of course, this requires more than a 3-axis machine tool. This only works for 4- and 5-axis machining centers. So to set up NX CAM in the geometry view, we need to have multiple machine coordinate systems. And I'm going to go through them here, and then we'll go through an actual demonstration in just a minute. So to set that up, we have an MCS mill that is really the tool change point, or the machine home, the Z0. Actually, the machine home is probably the best description. So we start out with an MCS mill that is actually at the machine home. Then we have a secondary MCS that is on the part. We're going to call that our G54 in this case, but it could be, just a work offset. And then under that, we start specifying additional MCSs. Now these additional MCSs are rotated off of the G54 offset. So these are set up as local coordinate system rotation MCSs off of the G54. So in this example here, I've got a MCS for the green face, and then I've created a cavity milling operation with the tool axis perpendicular to that green face. Then I created an MCS mill with the tool axis perpendicular to the yellow face, and then I created a cavity milling operation with the tool axis parallel to that yellow face. Now remember, what these MCSs do is they tell the system I'm creating a new work plane to allow my code to be much shorter once the tilted work plane has been described in the NC code. It's a little bit complicated to describe, so let me just show you how this works inside of NX. Let's get started. In CAM Express, I have created 4 different operations. These are all cavity milling operations, so they're 2.5 axis only operations. The first one I called cavity milling green because I'm machining this green face. The second one is called cavity milling blue because I'm machining the blue face. And then brown for this brown face over here. And then finally yellow for this yellow face. Now these operations are really not unique. There's really the only thing I think I did that was actually different than you would do in a typical operation is I specified the tool axis vector as normal to a face. So I simply went in here into the vector dialog and I chose this face, and that makes the tool normal to that face, which means that I'm getting tool axis output in the direction of that face. So that's really the only thing special I did to these operations. Other than that, they're typical cavity milling operations. The uniqueness, or the thing that you need to set up as an NC programmer, is actually in the geometry view. So in the geometry view, I have multiple MCSs. The first one defines a couple of things. It defines that this is the main coordinate system. So this is the one that actually is the machine 000, or the machine home, whatever you want to call it. I also created a clearance option as the sphere, so you can see that whenever I clear out of that, I have a sphere that describes clearance zone that gets me out of any danger when I want to rotate the part. Then I created the workpiece, and of course the workpiece contains the part in the blank geometry. Then I created a second MCS, and I call this one G54. Now this one is a local coordinate system. There is no special output. I'm calling it fixture offset number 1, which should give me the G54 output. And then of course for the clearance, I'm simply inheriting what was created in the original MCS. Then I created 4 other MCSs, 1 for each face. And I'll just look at the green one first. For the green MCS, what I did was I made it a local coordinate system, but I changed the special output to coordinate system rotation. And that's the only thing I set here. Everything else is being inherited. So what this allows me to do is set up a coordinate system designed to create a tilted working plane on that green face, so that I get the output that I need. Now the best way for me to demonstrate this is to actually pull in one of our sample machines. So let me do that. So in the machine tool view, I double click on generic machine. I choose to retrieve a machine from the library. I'm going to choose the Simulation 7 machine with a Siemens control. The reason I'm choosing this machine is it has a rotary table to mount the fixture on, and then also a rotary head so you can see all kinds of motion going on. Choose OK. I'll specify the positioning as part mount junction. I'll set the part mount junction at the bottom of this holding device, this chuck. I have to set the selection content to entire assembly. Move the part mount junction there. Choose OK. Choose OK. I get a informational message. We brought in some pockets and we put those tools in those pockets. And here is my machine tool, all loaded and ready to go. Now, before I can actually simulate the NC code, I need to do a couple of things. First, I need to go into the machine tool navigator and identify my setup as far as the part and the fixture. So I simply double click on part, choose the geometry that represents the actual machine part. I would do the same thing for the blank geometry if I had one. For the fixture, double click on that, choose the fixture. The other thing I need to do is back under the Operation Navigator, under Geometry View, I need to set this MCS mill object as the machine home. So I double click on it to edit it. I say I want to specify the machine coordinate system. I choose that center point. I change the selection intent to the entire assembly. And then I pick the center of the mounting point for the spindle. And that's my machine home. Choose OK. And now I should be able to simulate the entire program. I'll step through this fairly slowly so you can see. I'll change this to machine code simulate so you can actually see the machine code being generated from the postprocessor. And then we'll simply step through this fairly slowly. I want you to see the code that Siemens controls need for work plane, for tilted work plane. Here we go, now we're getting into it. We rotate the B axis and the C axis. We then use cycle 832. And then as we step farther, you can see the Traore. Using the G54, we're going to orient the machine coordinate system, orient the axes, translation and rotation, and then we begin actual machining. So I think from here on I can just play this. So there it's machining that first face, roughing and finishing. And then as it finishes, it will back out of its zone and then move to the next face, establishing a new tilted work plane to machine it. There it's backing out, reorienting, creating the new tilted work plane, and performing the next machining process. And it'll continue to do this until all of the program has been run. So that's how you set up tilted work plane inside of NX or CAM Express. This is an example of FNUC output for tilted work plane. This is only one example. They can also use G68.1 or G68.2 depending on the parameters you set. In fact, I thought about trying to display all the different parameter settings for each of the three major control manufacturers, and I decided it was just too many parameters and too many options. So you can Google FNUC tilted work plane manual, and you can find the manual. You can do the same thing for Heidenhain and Siemens controls if you really need to see the down and dirty details for each type of control. Here's an example for Heidenhain. As you can tell, they do it completely differently than FNUC. They use this plane spatial command to specify the tilted work plane. And then a Siemens 840D example, We use priori, orient machine coordinate system, orient axes, and then a translate. AROT is additive rotation, so we're basically adding this rotation to the previous rotation that was already in the existing machine coordinate system. And then to close it down for a Siemens control, we set the translation back to 0 and turn priori off. So to summarize, in this lesson you learned about what a tilted work plane is. We showed you how to set up a tilted work plane for NX or CAM Express. And then we tested that example setup to make sure that we were getting good simulation from our built-in machine tools. Thanks for viewing. Our next lesson will be on user-defined events.